presentation, the Arthur Holmes Medal Lecture by David Gubbins, Buoyancy in the Earth's Core and Possible Melting of the Inner Core.
Okay.
And this one was mine. And that's
okay. Okay, this is the Arthur Holmes lecture. I'm going to be talking about something completely different. This is a global cooling lecture, which, as most of us know, that the important bits of the Earth have been cooling for the last 4.5 billion years since its formation. And my talk will be directed mostly at its influence on the liquid core and the magnetic field. As it's the Arthur Holmes lecture, I should mention something about Arthur Holmes. I started my PhD in Cambridge in the Department of Geodesy and Geophysics, where plate tectonics was more or less then most of the developments had just recently been completed or were underway. And that department made a big contribution towards the development of plate tectonics. Unlike one of the other departments in Cambridge, the geology department, for which the discovery of plate tectonics lay a decade or two in the future. But in that department, there was a bright young spark who was John Dewey, who would occasionally cycle out to Manningley Rise and tell those of us he regarded quite correctly as arrogant physicists that geology wasn't difficult, you just had to give it your time and read about it, and the best thing you could do is read Arthur Holmes' book, which I did. And anyone who hasn't read it, I commend to you the first edition, the edition that was written before the great discoveries of marine geology made things rather more obvious than it was to continental geologists beforehand. But a remarkable man. Okay, Kelvin had the idea that the Earth was cooling, and he used that to calculate an estimate for the age of the Earth, which is equally famously known to be wrong. And I was told at school that that was because Kelvin didn't know about radioactivity. But that is actually wrong. At least it's something of an apology. When you look at what Kelvin did, he assumed the Earth was formed hot and then cooled by thermal conduction as a solid sphere, and use the temperature gradient at the top to estimate the time for which it had been cooling, essentially a skin depth calculation. And it's convection that makes that wrong. The thing that wasn't included was convection. This picture actually is something that would not shock Arthur Holmes. And the reason and the heat loss from the Earth is essentially not only governed by convection, but you really don't, radiogenic heating plays an important role, but not a dominant role in the Earth's thermal history. So if we look at the estimates of heat loss throughout the Earth, then observation gives us this figure of 44 terawatts. Now, this hasn't been challenged for perhaps 20 years now or more. But that doesn't actually make it any better an estimate than it was 20 years ago. And it's actually probably less certain than we might think. The observations are not just based on surface heat flow measurements. They also include contributions from the heat loss at ridges, where mantle material rises up to form new crust. And that estimate is very much model dependent. It depends on how rapidly the plates are moving apart, and it depends on a model of plate tectonics. And also, hydrothermal circulation plays a role, which is also rather unknown. These numbers have been taken out of Frank Stacey's book, so they represent, well, this is the word. Frank is not here, I hope. I don't think he'd like to have this adjective applied to him. But this is, would be a commonly accepted picture by most people who don't work on the core. So you first estimate the radiogenic heating in the rocks you can get at, and this number dates from Taylor and McLennan. And it, again, is an old number, but one can do quite a good job because you can actually examine these rocks and measure how much radiogenic material there is in it. In the mantle, we have no direct samples, so you have to rely on meteorites, but the mantle is there's not much radiogenic material in meteorites, but mantle is a very big place, and so you get quite a big contribution. And then, for most of the last 40 years, most people don't believe there's any radiogenic heating at all in the core. My guess is the present vote is about 40-60 against, but zero radiogenic material in the core. I'll come back to that a little bit later. And then secular cooling of the whole Earth, 10 terawatts. And if you work out how much of that's coming from the core, you end up with just 3 terawatts going across the core mantle boundary. And that sort of picture leaves you with a slow cooling of the Earth of tens of degrees per billion years, which doesn't upset anyone and doesn't present any awkward things to explain in the distant past. Now, the trouble is that I don't think, and I think most people would agree with me, that you can generate a magnetic field with that little heat coming across the core mantle boundary. And the dominant reason is a very simple one. It's just that the temperature gradient in the core is very steep, and iron is a very good conductor, and you conduct an awful lot of heat down the adiabatic gradient. And the estimate of the adiabatic gradient is worth going into some detail as to how this is done. It's determined from GRUNEISSEN'S parameter, the thermodynamic parameter gamma, which has recently been calculated from what is called first principles or ab initio calculations, quantum mechanical calculations, and has produced this value of 1.5, which is now in some substantial agreement. I'm not saying it's going to stay that way for a long period of time, but there is a general agreement that GRUNEISSEN'S constant is 3/2 pretty much throughout the outer core. And then if you rearrange this thermodynamic definition, you can get a useful formula for the temperature gradient involving GRUNEISSEN'S constant, the acceleration due to gravity, and the seismic parameter, which in the core is the square of the acoustic velocity. And of course, we know these two things extremely well from seismology, and so probably we know the logarithmic logarithmic gradient of the temperature in the core very well. And I would say the most uncertain thing about this, in this formula at the moment, is the temperature here, because in order to integrate it, we need a tie point where we need one temperature somewhere. And the place we choose is the bottom of the liquid core, top of the solid core, where we presume this is a melting transition, and we can estimate the temperature there. That's also been subjected to calculations recently by the group at UCL for liquid iron at core pressures, and that value is in agreement with the shockwave experiments. It's not in agreement with a diamond anvil static experiment, and that's a matter for resolution still. But these numbers come out to be about 6,500 degrees, and then that temperature is reduced because the outer core is not pure iron. It contains a significant amount of other elements which will lower the melting point by about 1,000 degrees. And so you end up with temperatures of the order of 5,000 degrees or give or take a few hundred degrees. So I would say integrating that equation gives you a curve, and I would favor this solid line along here, tied into the temperature at the inner core boundary, which is out about here. And the thing I want you to notice about this is the steepness of this gradient increases with radius. And that's quite important in what I have to say, more important, I would say, than the absolute temperature. Of course, we have some more constraints, fortunately, here, in that you don't really, this is the core mantle boundary, and you don't want to melt the rocks at the core mantle boundary. Perhaps, actually, there may even be some people here who do, but generally speaking, it would be a bad idea. And the reason that it steepens, when you look at the numbers here, is because g, the acceleration due to gravity, is much bigger at the core mantle boundary than the inner core boundary, and the seismic parameter is much smaller. And g over phi enters this formula, so it gives you a temperature gradient that is 3 times bigger or more at the core mantle boundary than it is at the inner core boundary. And when you multiply that by the thermal conductivity to get a heat flux per unit area, and incidentally, there's just, I should pause now for, I think, a commercial break, that the thermal conductivity and the electrical conductivities of liquid iron are probably now the most uncertain parameters in this subject, and it would be awfully nice if someone out there could tie them down a little better, as they have done with GRUNEISSEN'S constant. But the larger area, so you take this gradient, which is in degrees per kilometer, you multiply by the thermal conductivity, and multiply by the area, and you get 8 terawatts. So in other words, 8 terawatts is being lost by thermal conduction cooling the core. It's far greater than the 3 terawatts, which was typical of the values that are obtained from generally from mantle convection studies and people working from the top down rather than from the bottom up. And the heat flow across the inner core boundary is much less because it's a smaller area, but also because this temperature gradient is much smaller. So we immediately expect any convection going on in the core to be stronger at the bottom than at the top. And in fact, the top may even be stratified. Now, that's not the whole story. We know a lot more now also about core chemistry. We know that the inner core, this solid, is too light to be pure iron. It has to have something else with it. We know also that the outer core is too light to be liquid iron. And not only that, the outer core density is even less than you would expect from melting, which means that there is a higher proportion of light elements in the outer core than in the inner core. And again, the same group at UCL have done some calculations. I interacted. This is a slightly bizarre way to perform experiments in cyberspace. At one point, they were doing calculations of iron and sulfur mixtures, and I asked them why the concentrations were such funny numbers, and they said, well, we've only got 64 atoms, so the concentration has to step up in 64ths, which is the way these calculations are done. But they compared the free energies between the solid and liquid states of 2-component mixtures and found that for the elements sulfur and silicon added to iron, the solid state was quite, the free energies were essentially the same, which means that the composition of the solid was the same as the composition of the liquid. Now, this actually is a surprise, and it's only true at these high pressures pertaining in the Earth's core, because at lower pressures, the sulfur will certainly separate. And so it cannot, the implication is that you can't use these elements, which are commonly believed to be constituents of the core, to explain the density difference between the inner and outer cores. Oxygen, on the other hand, when you do the same calculation, you find that almost all the oxygen remains in the liquid. And my simple-minded way of understanding this is that the size of the sulfur and silicon atoms are about right. to fit into the solid iron lattice, and the oxygen atoms are not the right size. But that rather, that's not to suggest that you don't need to run the supercomputer for weeks on end to do the calculations properly. Okay, so this is just a summary of how you could make up the two cores. You start with a density of solid iron at these pressures and temperatures. You add 8% of sulfur, and you would get down to the density of the inner core, as seen in common seismic models. You then melt it, and it gets a little bit lighter, but not light enough, and you have to add the 8% oxygen now to get the density of the liquid iron core determined by seismology. So the important parameter then is this density difference between the inner and outer core. That is a crucial parameter, and it's not very well determined because seismology isn't very good at determining density. It's much better at determining seismic velocity. And a few years ago, I persuaded, my role in this job was to persuade Guy Masters to redo his PhD thesis of 1980, and so he did the work. And I think of the two of us, I got the harder job, but I did manage it. And so he redid this estimate of the density jump at the inner core boundary using normal mode data and came out with a density jump that was a bit bigger than PREM. I say significantly here. Those of you of a statistical bent can decide whether or not one standard deviation is significant, but it's bigger. But the effect of that increase in density jump has a huge effect on the composition, because you're talking about it's 0.2 grams per cc on 0.6, but some of that 0.6 is due to melting. So it almost doubles the amount of oxygen you need in the outer core. That, because you've got more impurities, will lower the inner core boundary temperature estimate. But more importantly, it helps power the dynamo. So to complete the picture of how we think the dynamo runs, and I say we, I don't think this is particularly now controversial. I think most people have this same model in mind. I would call it a standard model, is that on freezing of the liquid at the bottom, you release light elements. I've mentioned oxygen. Those light elements then are buoyant and rise and help drive the convection. This so-called compositional convection is much more effective at generating magnetic field than heat. And that's because if you release heat at the bottom, most of that heat is just taken up by convection, quite apart from the conductive loss. Convection just takes a lot of that heat up and gives it to the core mantle boundary without really doing anything else. On the other hand, the energy associated with the potential energy that is lost by this light element rising has nowhere else to go except to be dissipated as heat, and it's dissipated through mostly the magnetic field. So if you like, this stuff just stirs the core. It's like putting a spoon in and stirring it up, and that powers the dynamo. Lastly, radiogenic heating in the core, the popular isotope that's normally talked about in the core is this isotope 40 of potassium. If you include radiogenic heating in the outer core in your model, then it doesn't actually help generate magnetic field very much, because it's just heat for a start, and it's also distributed largely on the outside of this sphere, towards the outside. It's uniformly distributed, but most of it's in the outer radii. And that doesn't really help drive the dynamo. What it does do is keep the core warm for a nice long time. So the primary effect of this potassium is to keep the core warm. Because, that's interesting, because these heat losses are so great that the inner core freezes very rapidly, and most of these calculations I can show you have the inner core forming, going back in time. The inner core forms 1 billion years ago, or thereabouts. And that's a very common feature of all the calculations coming out now. And if you by adding potassium 40, you can keep the core warm, and you can extend the age of the inner core. So there's no radioactivity in the core. This is one of my calculations, but it's typical, I think. The numbers are typical. The present cooling rate going across the core mantle boundary is about 9 terawatts, and all of that's coming from cooling and latent heat of freezing at the bottom. A cooling rate that is some 60 degrees per billion years more rapid than, of course, because the whole Earth is cooling faster. But as I say, the inner core freezes very rapidly, so you have to find some other way of driving the dynamo without chemical convection in the distant past. But we don't know much about the distant past, and so it can actually be done. I confess I don't like it much, and I probably shouldn't be telling you that because I don't think you should be particularly interested about my sense of aesthetics rather than any scientific result. My calculations give the same thing. If you put lots of potassium-40, and this is an awful lot, into the outer core, and that amount was calculated in order to make an inner core age of 3.5 billion years, you can do it. And there is at least one person who quite likes this. Ramamurti in Minnesota quite likes that amount of potassium in the outer core. So those are the sorts of calculations that go into what I would call the standard model for the Earth dynamo of driving it and keeping a magnetic field going for the whole of Earth history, because we seem to have had a magnetic field for that long. And I want to talk about some interesting effects. I should perhaps pause at this point and explain that unlike the atmosphere and the climate, this is a subject which doesn't have an awful lot of direct observation. And so observations are precious, and they really control our speculations. So heat loss from the core varies a lot from place to place, and I think that's an extremely important influence on what we're looking at. Everything is controlled by the mantle. The mantle determines how rapidly or how slowly the Earth cools, and it determines how much heat flows across this boundary at the bottom, which it sees as a constant temperature boundary. Now, fluid in the Earth's core moves 100,000 times faster than mantle flow. And so this core fluid is rushing around, equalizing the temperature on the bottom. And if you do a mantle convection calculation, you will actually you should properly use a constant temperature down here. And because it's a convective system, that means that as the heat flux across this boundary sets itself in response to the flow. And we will have a variable heat flux, and we can actually say something about the temperature in the mantle in two ways. One is from the seismic velocity. So that's what this map is. And the seismic velocity map of the bottom of the mantle is dominated by this fast ring. This is shear wave velocity. And shear wave velocity is known to vary with temperature. So this ring, which is beneath the Pacific Rim, the Ring of Fire, is associated with subduction that's been going on around the Pacific for at least 100 million years in the same sort of geometry. And so it's cooled the whole of the bottom of the mantle off. And it's quite reasonable that this ring should be cold. This so-called lower mantle donut, and the strawberry in the middle is slow. This is an interesting subject in itself, of course, and there will be people here who are working on this problem. The question is whether this is really influenced by temperature on composition, and the feeling at the moment, as I understand it, is that the high velocities are probably cold material. And while stuff is probably hot in these other regions, it may also be, the variations in seismic velocity may also be caused by compositional changes with heavy material just sitting down there on the core mantle boundary. But if that sits down there for long enough, it'll get hot anyway. The other way of doing this of estimating the heat, so let me just do the next step, that if we regard this bottom here as a thermal boundary condition, and we have a constant temperature on the core mantle boundary. It's cold here. We have a high heat flux, hot here. We have a low heat flux. And so we can use seismic velocity as a proxy for the heat flux across the core mantle boundary. The other way to estimate the heat flux is to actually do the mantle convection calculation, and that's also been done. And these and gives you an independent estimate. Now, what's interesting about this is that the magnetic field, which is here, I've squared it on the core surface, seems to follow this ring of fast velocity around the Pacific. Now, the magnetic field is dominated by rotation, and its latitudinal variation is presumably determined by the spin axis rather than by anything that the mantle is doing. And so we really should remove the variation in latitude of these functions and look at the variation in longitude, which I do here just by integrating the two things we've been looking at before. And you can see these maxima, the maxima and the shear wave velocity and the square of the magnetic field, do coincide in longitude. This is about the longitude of Siberia, and this is about the longitude of Canada. And the other thing I'll refer to in a minute is to note that the Siberian anomaly is actually much bigger when you integrate it than the Canadian side, and that is another issue of interest. There's a very simple physical explanation, simple in the sense that you'll be happy with it if you don't think too hard about it, as to why this should be. Where the heat flux is high, this is where the mantle is cold, this is where you expect core fluid to be downwelling, and where it's hot, you expect fluid to upwell, and the horizontal flows are really there to just maintain a constant temperature on the boundary. The second stage in the argument is that if you then have magnetic field lines poking through the surface, magnetic field lines are tied to some extent to conducting fluid, and therefore they ride along as on a conveyor belt on these horizontal flows, and they get pushed towards the downwelling and concentrated and create strong vertical field of the sort we've been looking at over the cold bits of mantle, and they get pushed away from the hot regions to form a bald patch where there's a shortage of magnetic field lines. And we can get more sophisticated now and do a numerical simulation of the geodynamo by solving all of the dynamo equations. Nowadays, it's not a particularly big calculation to do. And this is the model, this is one model I've done. There's a number of studies that show this correlation, but this was specifically designed to force the magnetic field that we generated to be as stable as we could possibly make it. And what we find in this configuration is a concentration of the magnetic field at the surface into 4 blobs. And if you choose your right year and look at the Earth's magnetic field, you find these 4 blobs are in exactly the same place. By exactly, I mean they're within 5 degrees, which to me is very convincing evidence that the lower mantle is actually dictating the magnetic field that we see right now. I just have a word to say about why I chose 1750, and this is where I like to quote an apocryphal professor of modern history at Oxford University who was fond of saying that everybody knows that the last 250 years of European history has been anomalous. And so I'll say the same thing about the Earth's magnetic field, that in fact in the last couple of centuries this region in the southern hemisphere has blown up. This is where magnetic field has the same sign as the northern hemisphere. It's associated with the fall in the dipole. And it's an unusual feature that you don't really find very much in paleomagnetism that's produced this north-south asymmetry between the northern and southern hemispheres. And this appears to be a rather more normal structure. I should say that that pattern also tends to appear in the long-term time average, the 5 million year time average of the magnetic field. Well, this model can also be used to do some more things and predict some paleomagnetic changes long-term. And this is the inclination anomaly, which is the angle the magnetic field makes with the vertical, minus what you would expect if the magnetic field were a dipole. And the scale here is in degrees. So this is a nice big scale that any paleomagnetist can detect. The accuracy of paleomagnetism is probably a degree or 2. And the interesting thing about this picture, apart from it looking like a death's head, is that the biggest variation in inclination anomaly is actually in longitude. And most effort so far has been focused on looking for differences between the northern and the southern hemispheres. And so really this is an indication we should be looking for longitudinal variations in the paleomag. And if we take one example and compare Hawaii here with Réunion, both of which are places rich in lavas that are suitable for paleomagnetism, then this data study of a few years ago showed a difference in the inclination anomaly, a slight difference between Hawaii in the northern hemisphere, Réunion in the same latitude in the southern hemisphere. And we see the same thing in the model, or similar, something similar, but looking at the model in detail, this is really a longitudinal effect and not a hemispheric effect. Okay, so this, again, lateral variation is still somewhat old hat, but how big are they? The message I would have liked to have conveyed to you so far is that lateral variations in heat flux on the boundary of a convecting system produce enormous effects. So how big are they in the core? Well, the variations in seismic velocity I've been showing you suggest something like 1,000 degrees peak-to-peak variation in the lower mantle. So that's quite a lot. In fact, that variation in the boundary layer in the mantle suggests variations in heat flux of about 100 milliwatts per square meter, and that's about the average. So in other words, the variation is big enough for in some places heat to be passing into the core, even though on average the core is losing heat. And that's confirmed by mantle convection experiments that I'll show in a moment. So let's look at what happens for the consequences from the dynamo model I showed you just now. This we've called the locked dynamo model because the magnetic field is relatively stationary and locked to these boundary anomalies I mentioned. That dynamo model had uniform internal heating and a fixed temperature lower boundary condition. The upper boundary condition was determined from seismic tomography using the seismic velocity as a proxy for temperature and heat flux. The heat flux variation here in dimensionless units normalized to 1 for the average heat flux over the surface had a 90% variation, so 45% either side of 1 heat flow out. And it's a fixed temperature lower boundary condition, but the solution will give us the heat flow across the lower boundary. And the interesting thing about the heat flux across the lower boundary is that it's in some places negative. So in some places, heat is passing out through the lower boundary, even though the average is substantial and the maximum is very large. So in some places, you've got heat actually going out through the bottom of this dynamo, even though it's cooling on average, it's cooling from the top. Well, why does this happen? Well, if we look at an equatorial slice of the flow, again, this is essentially a steady solution. So it's a nice, easy one to look at. You don't have to worry that you've been looking at it at the wrong time. Then we find that the downwellings are very narrow and vertical. These downwellings are associated with the Pacific Rim, and then this region here, where the upwelling, the very broad upwelling is happening, is the Pacific. So the fact that the downwellings are narrow means the heat flux variations are going to get concentrated as you go down. And also, of course, you're in a spherical geometry, so just from that simple observation, you would expect the heat flux variations to become greater as you go down. There's an area effect. One other thing I'll mention while I'm here is that the fact that these downwellings are vertical means that the heat flux pattern on the inner core boundary reflects the heat flux pattern on the core mantle boundary. And that's a surprise, and I'm not sure I believe it because our parameter ranges we can explore with these numerical calculations are very restrictive, and there's non-magnetic experiments, both laboratory and numerical, that suggest that for core parameters, you might expect these downwellings to spiral around in a rather spectacular manner and not simply be connected top to bottom. But certainly in the regime we're in at the moment, these downwellings are fairly near to vertical. And that may be important for observations that we come to next. We've done a number of dynamo models, by the way, where we try and make these downwellings spiral around, and the dynamo action invariably fails. Okay, I would like to scale this to the Earth. I've been trying to be very careful to talk about lower boundaries and not inner cores yet, because this is a dynamo model. Now, one thing we have to do to scale this to the Earth is take into account this heat flow down the adiabat I was talking about. And this is something, excuse me, that's been omitted from some of the calculations based on mantle convection up to now. The heat fluxes we've been talking about coming across the core mantle boundary are roughly half conduction down the adiabat. And most of our calculations have the convective heat comparable with this conducted heat. So I'm going to make a very simplifying assumption in the spirit of this sort of calculation and say that the adiabatic heat is the same as the convected heat, and in these dimensionless units make it 1. But at the inner core boundary, the adiabatic gradient is that much weaker. By a factor of it's only 0.3, and so the heat flux you have conducted at the inner core boundary is only 0.3 in these units. So if we subtract off, well, we now have to add on to the dynamo calculation the 1 terawatt and get these numbers, so we've proportionately reduced the lateral variations we had before, and so in terms of the Earth, a modest variation in heat flux across the core mantle boundary translates into a bigger relative lateral variation relative to the average heat flux in the dynamo model. Likewise, at the inner core boundary, we have to add our 0.3, and because we're adding so much less conducted heat, we still have here heat going down into the lower boundary. So I can even say down into the inner core now. So a consequence of what does heat going into the inner core mean? Well, it means it's melting it. There are some places where the inner core is being melted again, having only just been frozen, perhaps. Now, in this model, it was internal heating, and the heat crossing the core mantle boundary is actually much greater than the heat crossing the inner core boundary. So this is this model, which wasn't really intended to originally match the thermodynamics of the core. This model would correspond to one with lots of potassium in the liquid core. Okay, let's try another model. We've got plenty of them. The trouble is we suspect that the parameter ranges are not that great. So another locked dynamo model. This one has lots of bottom heating and internal heat sinks to simulate the adiabatic effect, the effect that conduction is taking heat away in the upper reaches of the core. And that properly maps into the dynamo equations as a heat sink. It's also appropriate for compositional convection as well. So in this case, we have a big variation of upper boundary heat flow. The average happens to be, excuse me, a factor of 2 was chosen. And in this case, the lower boundary heat flux is everywhere upwards. There's no implied melting of the inner core in this particular model. But the important thing to take away from this is that the lateral variation in this case is comparable, top and bottom, for this other extreme model. So it's dependent on whether, on how much heat you have going across the inner core boundary. Well, now let's shift and let's take some numbers from someone else, so we can't be accused of fiddling the numbers. This is taken from a mantle convection study done recently by Nakagawa and Takli, in which they do a very sophisticated mantle convection calculation in a sphere. They allow for a phase change. They allow for the post-perovskite phase change at the base of the mantle. They allow for, to some extent, of compositional variations at the bottom of the mantle. And I have to make one more assumption here, which is what the heat flux variation is at the inner core boundary. Well, I've shown you one dynamo where it was the same as the core mantle boundary. I've shown you one where it was 3 times as much. So now I'm going to take it to be twice as much. And in this case, we have these huge variations in heat flux across the core mantle boundary. We subtract off the adiabat, and they get even bigger. And we downward continue them to the core. Sorry, for this model, this is model 1, I've called it, no post-perovskite uniform composition. Inner core everywhere, freezing heat flow out. If we take, we'll call it their most sophisticated model because I don't know whether it's their preferred model or not, but it should be their most realistic model. It's my preferred model because it does what I wanted to show, that we make the same assumptions again, and in this case, we have a bigger range and a weaker initial average heat flux out of the mantle. That's equal to the adiabatic value, which is geophysically very reasonable. Don't forget, the adiabat's responsible for 7 terawatts as it is, so we've got an awful lot coming out of the core already. And in this case, we retain a heat flux into the inner core, causing melting. So I don't want to make this argument, I'm not trying to prove anything here, I'm just trying to raise the possibility that the inner core in some places is melting. And the important thing is not the speculation or to argue about numbers, which is not a really very wise thing to do. It's to look for observations, and for that we need some consequences. What would be the consequences of the inner core melting in places? And don't forget, because we've got very narrow downwellings, which are causing freezing, and they're dumping lots of mush in a relatively small area, and these very broad upwellings, then it means that it's quite possible that the inner core is melting over a large part of its surface, while on average is accreting. Well, these scenarios with melting involve low heat flux across the core mantle boundary, and that makes life easier to fit in with everybody else in the geophysical world who live above the core mantle boundary. The second thing is that melting will release heavy elements into the liquid core again. So you've not only got this light stuff coming off and driving the convection, you're also dumping lots of heavy liquid straight out into the bottom of the outer core. What happens to them? Well, it's possible that of course, the convection's vigorous enough to mix it all up throughout the outer core. But suppose it doesn't. Suppose it only goes up a little way. You then end up with this anomalously dense layer at the bottom of the outer core, and there's evidence in seismology that that's there, and I'll talk about that in a moment. The last thing is the inner core is a very inhomogeneous place. There's lots of seismic inhomogeneities, and these are really quite hard to explain because this thing has been sitting there like a sort of moon hanging in the middle of the Earth, doing nothing for the last 4 billion years except growing slowly, perfect crystal growing situation. Why should it have big lateral variations that we see in the seismology? Well, people have talked, of course, about variations in freezing rates at the inner core boundary, but why stop there? Why not just melt some of the stuff? That does real damage or real violence to the seismic properties because you reveal this pre-compressed, pristine material on the surface. This stuff has been buried, it's been under pressure, it's had all the pores and liquid squeezed out of it. And so I would expect it to have high seismic velocity and high Q in these regions where it's freezing. Of course, that's only valid if the inner core stays in the same place for a significant period of time. So you have to actually, for this to work, you have to have the inner core gravitationally locked to the mantle. Well, this stratified layer at the bottom is an extremely difficult thing to explain any other way because it's dense and it's got all this light stuff going through it that's light enough to not only drive convection, but drive the dynamo, generate the magnetic field, stir all the liquid up to better than 1 part in a million normally. So why should there be a dense layer down there? I've actually been with Francis Nimmo and Guy Masters suggested a mechanism which could do it, which is rather complicated, and it involves a sort of freezing melting process where the light stuff passes through by a zone refining, by a process akin to zone refining. But perhaps this idea of dumping heavy stuff in the bottom of the core by melting bits of it, bits of the inner core, is an easier way to explain this anomalous layer. The layer is observed not directly from density, but by low seismic velocity, and lower than is allowed by neutral density, and in a liquid of variable composition, then low density is associated with, high density is associated with low velocity. So I'll just summarize the message I would like you to take away, that lateral heat flux variations across the core mantle boundary are big, and they have a big effect. So they're not just something funny one's inventing in order to add an extra knob or complication to the problem we're studying. They are huge. Variations across the inner core boundary could be larger. That needs more exploration from dynamo models, and therefore parts of the inner core surface may be freezing, and it can explain a number of natural phenomena. Thank you. My time is up. Yes, I'm out of time.
Are there questions to this presentation? Please wait for the microphone to appear.
Of suggesting a latitudinal dependence on this melting to freezing activity that's going on at the inner core boundary.
Sorry, I didn't catch the first part of the question.
You stopped short of suggesting a latitudinal dependence. Have you considered that?
There will be a latitudinal dependence. I doubt it's large enough to produce melting. I wasn't just talking about longitudinal dependence. I was talking in general from this model, but I haven't actually, I mean, as you can see from the map of heat flux variation, there is a latitudinal dependence. It's just more dramatic in longitude.
Yes, go ahead. Please wait for the mic.
Could you comment on the issue of the superrotation of the inner core, which implies some kind of anisotropy of the inner core?
Okay, yes, I must admit, in the 80s, I wrote a paper with a title that should have been guaranteed of free of any kind of observational interference, which was called Rotation of the Inner Core, because I never thought anyone would ever observe it at the time. My understanding of this is, I mean, my original papers just said that we see a westward drift of the magnetic field of the order of 0.2 degrees per year, and so we would expect the inner core to be driven around by magnetic forces to that extent. Now, what has changed since then is, I mean, there are seismic observations which are disputed. There is, so the seismic observations suggested superrotations much bigger than that. I mean, it's inevitable in a dynamo calculation like this, if you put the magnetic force torque onto the inner core, that it will be driven round. It's superrotational just because of the dynamics of the core. That, I think, is understood. But if the inner core is gravitationally locked to the mantle for the same reason that the moon presents the same face to us all the time, then it will be just held there rigidly. Now, whether it's held there rigidly depends on its viscosity. But at the moment, while there's this dispute, I'm going to assume the simplest thing, which is that the inner core doesn't superrotate. I will say one more thing, and another very interesting observation made by Bruce Buffett and John Mound is of this 6-year period in the length of day, which looks awfully like the inner core's version of the libration of the moon. The reason we see slightly more than half the moon's surface is because it does this as it goes round. And this 6-year period in the length of day can be explained by the inner core doing the same thing, with the angular momentum being balanced out by the mantle doing the opposite, and that's causing this change in the length of day. So it's a very interesting subject, and it's still allowing us to assume the simplest thing.
Further questions? Yes, back there.
David, as you know, that the main argument for people looking from the mantle for a low heat flux coming across the CMB is a buoyancy argument, largely dynamic topography observed over hotspots. This number, of course, usually implies that there's a relatively low excess temperature in plumes, and actually something that I've always found puzzling, as you and I know, we have talked about it a lot. The key thing that I wanted to add was, if you go this number carefully through and investigate what this really means on lateral temperature variations deeper in the mantle, you come to numbers that are actually then implying quite realistically the same amount of heat flux going across the CMB that you independently want to have from the core. So a key thing that I want to drive home is you can look at the CMB from the mantle side and you would make careful geodynamic estimates that within a terawatt or two agree with the estimates that you would make.
Yes, I mean, I think we're on the same side here. I still would like to reduce the heat flux out of the core. And something I didn't mention is that the lateral variations means that you only have to have the core convecting and mixed everywhere. For that to happen, you only have to have it super adiabatic in one place. If you exceed the adiabatic heat flux anywhere on the core mantle boundary, then the whole core gets mixed. And so we can actually allow a substantial reduction below the adiabatic gradient for that heat flux. So we can go below 7 terawatts, if you want.
Okay, I think it's time to thank our last speaker. And before you disappear, there's a reception at the back of the room that's open for every participant in this medal session. I'd like to thank all the speakers and the audience for participating.